Last time, we watched what happens inside this process boundary when a device rotates. The activity is destroyed, annihilating the UI state. To fix this, we move state out of the UI into a container immune to this disruption. Understanding this container requires answering three specific questions. What is it? Who holds it between activity instances? And when does it finally end? Placing state here reconfigures how memory and ownership are structured in Android, shifting the burden of data retention away from the transient UI. Mastering this architecture is the only way to protect user data from arbitrary OS recycling and prevent silent state loss in production. This container establishes a strict division of labor. The activity is relegated exclusively to displaying the UI and routing user events. The view model has exactly one responsibility. It owns and modifies the state. Without a firm boundary, multiple UI components can silently overwrite data in unpredictable orders, creating race conditions. We enforce this boundary in code via the private mutable and public read-only pattern. The view model updates its private state and exposes that data as a public read-only flow. Because the state is protected and outlives the activity, a configuration change is no longer a threat. A new activity simply spins up and reconnects to the existing data. This creates an immediate performance impact. One network fetch can now survive infinite screen rotations without triggering redundant API calls. Assigning data a single, stable owner prevents state loss without the size and serialization constraints of a temporary UI bundle. Developers frequently cause memory leaks by imposing the wrong mental models onto the view model. A common error is assuming the application-level object holds the view model to keep it alive. It does not. Ownership is strictly local. Another error is the belief that view models actively monitor the activity lifecycle to make persistence decisions. View models are entirely passive. Briefly navigating away also does not destroy the view model. The most dangerous temptation is storing a view inside the view model for convenience. Because it outlives the UI, holding a view tracks the destroyed activity in memory. The garbage collector cannot clear it. This specific error is exactly what memory profiling tools are built to catch in production environments. Imposing active, reactive, or globally owned mental models onto a passive state container transforms a safety mechanism into an application-crashing memory leak. If the activity is destroyed, who is actually holding the state in the void between destruction and recreation? The true owner is the ViewModelStore. It is a distinct memory layer that explicitly holds instances. When you use the by ViewModels delegate in code, the activity acts as a temporary client. It requests an instance from the store. It never constructs one. Consider a complex screen requiring both a search state and a filter state. The store prevents state entanglement by holding two separate view models for a single screen. Because the activity is merely a requesting client, the store provides the unbroken architectural bridge across the void of UI destruction. We define the view model's lifespan using the logical stream. This represents the user's continuous session with a specific feature, independent of hardware state. Rotation dissolves the activity, but the logical stream continues unbroken. Pressing back signals the user's intent to permanently finish the session. This final end to the logical screen triggers the onCleared callback, utilized strictly for releasing remaining resources. Survival is dictated entirely by user intent to remain on the screen, completely insulating the data from the OS's internal habit of recycling UI objects. The defensive structure is now complete. The view model holds state, the store preserves it, and the logical screen defines its lifespan. However, there is an absolute limit, an event that bypasses all these defenses simultaneously. That event is process death. This occurs when the operating system terminates the app in the background to urgently reclaim system memory. Everything dies at once. There is no ViewModelStore left in memory to ask for data upon return. Yet there is a single architectural artifact designed to survive this total annihilation. This chip provides the minimal data necessary to rebuild the entire state from scratch. While the view model perfectly conquers UI rotation, true application resilience requires mastering how to reconstruct an entire process from one surviving chip. Understanding configuration changes is the first step. Building for true resilience requires mastering OS-level process management. We solved that problem in Episode 5. If this mental model of the view model clarified your architecture, subscribe to continue the path.